Okay.
Okay, so thanks for everyone who's logged in so far for coming. The session is being recorded and will be available on our YouTube channel or website or somewhere or everywhere. So if you miss anything, you can always go back and watch it. And I will do my best to monitor the questions. So if you want to ask a question at any point, I guess you can push a button and make a question. So today we'll be talking about Cosmic Pi, which is a distributed muon detector, a fully open hardware project to try and democratize access to cosmic ray detection using cutting-edge technology. So moving on from Geiger-Müller tubes to use scintillators. This scintillator here, it's all wrapped up. And also SIPMs to really take what is used in large-scale physics particle detectors like ATLAS and CMS at CERN, and to simplify it so that you can have one of these in miniature on your desktop. Today we'll be talking about a little bit more kind of the foundations for this project. Itam will be taking us through the physics behind muons and detecting muons. I'll then give you a brief tour of the hardware, so how we got to our current iteration. The members of our team, we've been going since 2014, so there's quite a lot of people who have contributed over the years. A little bit on the performance of our current design, the electronic circuits that we use, which is kind of really the beating heart of the detector. A very short overview on the firmware, which makes it go, and the higher level software, which runs on the Raspberry Pi. That is what most people see when they log into a Cosmic Pi. Some words on our centralized infrastructure. So we have an MQTT server, and all the devices submit their events to it on a more or less real-time basis. And then a cost breakdown from our last production run to give you an idea of how much it actually costs to build your own device. So what is a Cosmic Pi? It's a detector for muons, which are a type of cosmic ray. And from the Pi name, it includes a Raspberry Pi. So the current iteration, we use a Raspberry Pi 0W, which is the smallest, cheapest, most basic Raspberry Pi you can get. It costs about, I think it's about £8 or £10 in the UK. Pretty limited, even with kind of all the advances in technology, but very cheap. And this kind of fits in with the ethos of building the lowest cost detector we can with the highest performance. And the other kind of fundamental part of the project is that it's completely open. So all our hardware is open, licensed under the CERN Open Hardware license, and all our software is open, licensed under GPL. And we started off on the CERN Open Hardware repository, and now we've got everything hosted on GitHub. So anything that we have produced that we've decided is finished or almost finished is available for anyone to look at, read the code, and understand and contribute. So that's kind of the fundamental background to it. What motivated me, and I think the rest of the team, was that at the time we started this, I'd been working at CERN for 4 years. And as an electrical engineer, I had no idea how to actually build a particle detector. And being curious, I wanted to learn how to build a particle detector from scratch, and the whole thing. So the triggering system, the scintillators, the sensors, the analog, the digital, the high level stuff, the data representation, to be able to kind of at least have a small insight into the whole thing. And I knew a little bit about electronics by teaming up with other people who knew about physics and building detectors and IT. Together, we were all able to kind of see the whole jigsaw puzzle and put it together. And it's been a fun journey so far, and it's not over yet. So I think now I'll hand over to Itam to talk about the physics.
Okay, so the first obvious question would be, what are these cosmic rays we're trying to detect? All right, and so on this slide, you can see a nice, I don't know what it is. Is it a quarter of our Earth, planet Earth, and then several things which are basically incident, let's say, on our Earth or our Earth's atmosphere. And so you can see, I don't know if you can see the rightmost red zigzaggy line, the photons. So these are essentially what we see with our own bare eyes. We can see stars, we can see various, we can see our own sun, of course, we can see the moon, some planets, and so on. So these are the first things that were observed, all right, coming from outer space. And they also still represent to this day a huge, let's say, amount of effort in trying to understand and learn about these, let's say, celestial objects. Now, I'm going to continue with the neutrinos, which are essentially neutral particles and which interact very, very little with matter. They're also produced in various places, such as the sun and so on, stars, and they basically, because they're very weakly interacting, we had quite a lot of trouble, essentially, detecting and determining their properties, and we still have these issues, and this is actually my sort of domain. I work mostly with neutrinos, and I build neutrino detectors. Now, cosmic rays are quite interesting. For a start, the name itself is a little bit misleading. The name was given to these particles at a time when physicists believed that these were rays a bit like photons. All right, a ray is basically a continuous stream of something. And we thought they may be electromagnetic in nature. But in actual fact, these things are particles, all right, individual particles with a lot of energy. And as you can see from this little graph, 99% of these particles are actually nuclei, which are stripped of, well, atoms which are stripped of their electrons. So the core of an atom, the nucleus. Most of them are actually just a proton. This is the lightest element we have. 90% of these nuclei are protons. About 9% are the second heaviest element, which is helium. Physicists refer to helium usually as outer particles. And then the rest, so a tiny fraction, will be heavier elements, all right, all the way up to, for example, iron and even beyond. And of these cosmic rays, then a tiny fraction would be electrons, about 1%, and even smaller fraction of stable antiparticles, such as antiprotons or positrons. Antiprotons, which are obviously the antimatter equivalent of protons, and positrons, which are the antimatter equivalent of electrons. So there you have it. That is the picture. Cosmic rays were first discovered in 1912 by a physicist called Victor Hess, and he did that by sending balloons high up into the atmosphere, because all ground-based detectors of the time obviously could not or would not measure cosmic rays. One of the challenges of cosmic rays is that because they interact with the atmosphere, they essentially, well, you could call it disintegrate. Okay, they disintegrate and produce showers. So their energy is converted into other particle types. And so what we can observe, for example, on the surface of the Earth would typically be muons. So I'm trying to activate the next page. James, could you switch to the next slide? It seems to be, thank you. Yeah, I don't know why, but I'm still in remote control, but it's not showing the slide. Okay, so a couple of bits of information. Don't get too worried about the, let's say, the units, okay? I just want to give you an idea of the differences in scale. So these cosmic rays basically have very, very wide energy spectrum. So the peak of this sort of distribution of energies is around 300 MeV. That's 1 unit of energy, if you like. Now, but the highest observed energy is about 1,000,000,000 times higher than that. So that tells you that these are really, it's a huge energy spectrum, all right? All sorts of particles, and that tells you also that the origin of these particles is very, very diverse, all right? The highest, if you take, for example, photons, the highest energy photons you can observe are about 1,000,000 times lower in energy compared to the highest energy cosmic rays. So these cosmic rays are a really important source of diverse objects. The other thing that I wanted to compare here was the highest collision energy for a man-made accelerator. All right, so this is the LHC. James knows it very well. It's the accelerator at CERN in Geneva, and it's the most powerful particle accelerator in the world. And here you have a maximum collision energy of 14 TeV. You have converted it into these 300 MeV units, so you can see more easily. And so that's 1,000,000 times lower in energy compared to this highest energy particle observed. This is, by the way, the OMG is the oh my god particle, okay, detected in 1991. So, so there you have it. Very interesting particles, can tell us a lot about the universe. So the one thing we want to do is try and detect them, if possible. So James, I'm going to have to ask you to change slides again, because my remote control is it's a bit like these. Okay, great. So these cosmic rays, as I mentioned, disintegrate upon reaching the Earth's atmosphere. And so they produce secondary particles, muons, and other secondary particles, but we detect muons at ground level, okay? And the rate is roughly a muon per square centimeter per minute. So it's actually, I mean, for a neutrino physicist, it's actually a pretty high rate of particles. So in neutrino physics, we build huge detectors, and we detect a particle a day sometimes. It depends what energies we're hunting for, what particles we're hunting for, and so on. If you're looking at tau neutrinos, for example, there's some experiments that have been running for several years and detected only a handful of these tau neutrinos. So that tells you that with such a rich amount of particles detectable on the Earth's surface, we could actually do something, right? And so, but it is still a challenge for a team to come up with a simple, it's not simple, but simplified and affordable detector. And so this is what we're going to be addressing with Cosmic Pi. So next slide, please, James. So, so this graph or figure shows you an incoming particle on the right-hand side. And this particle basically hits an object. This is a plastic scintillator, and it essentially deposits energy. So this particle will deposit energy in any material. We've just used a plastic scintillator here because that is the choice of detector that we've made. It's actually a relatively low-cost detector, which is it's now optimized. It's very well, let's say, suited for the detection of muons. So in the scintillation process, atoms in this plastic scintillator will essentially absorb the energy of your muons, a fraction of this energy, these atoms get excited, all right, by this energy that's just absorbed, and they release photons through a de-excitation process. So as they go back to a more stable state, a lower energy state, they release photons, and so this light can be detected by photosensors. And so the photosensors that we have chosen are silicon photomultipliers, which again are, let's say, a bit of a revolution in particle physics. They came along about 15 years ago. One of the first experiments that used them is the T2K experiment at its near detector site. And it went online around 2006 or so. And it uses several tens of thousands of silicon photomultipliers. So to get to that point in technology required obviously quite a lot of research and development. And so now these plastic scintillators coupled to silicon photomultipliers are very, very affordable, and they can be mass produced. And so it's an interesting tool to be able to use so that we can actually detect these muons. A few more facts here. The muon itself in this type of plastic will deposit a small fraction, as I mentioned before, about 2 MeV per centimeter. So you can do the maths with a peak at 300 MeV. These are cosmic ray peaks. I mean, the muon, let's say, peak energy for muons reaching the Earth's surface is much higher. It's about a few GeV, 4 GeV or so. So it would take several meters of plastic to stop fully a muon. The trick now for people designing these types of detectors is to efficiently collect the photons produced. So through a centimeter of plastic, you're producing several thousand photons, but you cannot collect all of those photons. So you need this silicon photomultiplier to be sensitive to a photon. Okay, you might be collecting 10, 20, 30, 40 photons, but it has to be sensitive to just a few photons. And so that really is the difficulty and the challenge for our type of particle detectors. Next slide, please. I think the next slide will show you essentially a photo of one particular, let's say, geometry of plastic scintillator. What you can see here is the central white bit. So the plastic scintillator here is actually a bar. It's about 1 centimeter large, a bit less than 1 centimeter thick, and 20 or so centimeters long. Through the middle of it, you have a wavelength shifting fiber. It's an optical fiber, a bit like the type of fiber you have in your home, bringing you the internet. And it's designed to essentially collect photons as close as possible to the area where the muon would have gone through this plastic. And it'll collect these photons and take these photons to the ends of this bar, which you can see, let's say, have these black connectors. And I don't know if you can see this, but on the left-hand side, you have a slightly shiny circular area, which is where this light would then be collected by a photosensor. So I think that is it for me. Back to you, James.
Okay, thanks, Ethan. So on to the next slide. There we go. So that's the physics of it. In terms of what that looks like in a detector, here we have a fairly generic block diagram of our system with all the different components, physical, sensors, electronics. So we have our scintillator. The scintillators in the latest generation look like this. So this is a plastic polystyrene-based scintillator. You can't really even tell what it is. It just looks like a transparent block of plastic, but it has a special chemical in it that makes it scintillate. So we have 2 of these. An SIPM. So I've got them in a little static proof bag, but in here, there are some very small 3 millimeter by 3 millimeter silicon photomultiplier sensors. These are from K-Tech, which we use in our most recent iteration. We have some analog amplifiers. So this is from an older design, but here we have a couple of op-amps, very small analog devices, chips. So they take the signal, so the muon hits the scintillator, it makes a few photons. The SIPM will convert those photons into a very small electrical pulse. That small electrical pulse is amplified by the analog amplifiers. And then we have a trigger system. So all of large physics experiments have some kind of triggering system to separate the signal from the noise. So what we do is we have a coincidence trigger. So we have 2 of these slabs stacked on top of each other, and we operate a trigger. So we collect data only when we see a signal in both the top and the bottom slab. as a way to exclude any noise. Another very important component is the DC-DC power supply. So these SIPMs that we have here have a breakdown voltage of 24.9 volts. So typically we operate them a little bit above the breakdown voltage in order to make them most responsive. They have a function of the gain as a function of voltage increases kind of from breakdown and slightly above. So we can't reach that obviously with a standard 5-volt power supply. We need to have a DC-DC boost to get us into the kind of up to 40 volts, gives us some margin for temperature. Then something special to Cosmic Pi, we've put some additional sensors on the board. So we have an inertial measurement unit, we have an accelerometer, a magnetometer, and also a gyroscope on the most recent design. This enables us to say, have someone install the unit the correct way up, or did they put it in upside down or on its side or back to front. Also to measure magnetic fields to check that they're not operating it within a strong magnetic field, that it's just in the Earth's natural field. We have a humidity and pressure sensor, which enables us to look at the environment. One of the things, there's a problem with these scintillators. They're great and they're nice and they're cheap, but they are sensitive to humidity. So by having a humidity sensor in the box, we can check that the detector is operating somewhere sensible. Someone hasn't put it in the shower. And then finally, we have a GPS. So this gives us the X, Y, and Z locations, but most importantly, also the timestamp. So we use the pulse per second, which is a common output from most GPS modules, to synchronize Cosmic Pis in a network. All of this plugs into your microcontroller, and this handles the hard real-time part of it. So detecting events, timestamping, and once a second in our architecture, it gives a readout to a Raspberry Pi, which then processes that information and makes it available. I see there's a question from Andy. How selective is a scintillator? What else can it detect? And how do you filter for only muons? How many muons come from cosmic rays versus other sources? Maybe E10.
Yes. Okay, so if you go back to the slide showing cosmic rays, okay. So, so the question, I haven't seen the question itself. So it's basically how selective, right? How selective is a scintillator? How many muons do we get from other sources?
Is that versus cosmics? And how do we filter for only muons?
How do we filter for only muons? In terms of hard numbers, I would say that it will depend on the purity. The first thing that can generate a fake signal, so a non-muonic signal in your plastic scintillator, would be impurities in the plastic itself. Okay, you can have some isotopes of some light elements, which exist in nature in quite large amounts, for example, potassium and so on, which can generate energy in the scintillator, which will then excite the scintillator atoms and release photons. So that will depend on the plastic. In general, these hits are much more rare than a muon from a cosmic ray event. So that's the first, I would say, source, all right, of non-muon hits. Now, how many muons from other sources? So muons typically would be generated from the decay of other unstable particles. All right, this is exactly what happens in the atmosphere. Your cosmic rays will probably interact with an atom in the atmosphere. They'll probably first produce directly actually pions, which then decay into muons. And a similar process might happen also at ground level. So if you have sources of radioactivity nearby, you may be producing muons. In general, this, apart from if you, for example, close to areas, for example, you can produce radon. You have radon production, which is quite high in some areas, close to mountains and so on. Your rate of muon production from radioactive sources, which are let's say, cosmic in nature, is going to be negligible compared to cosmic rays. So it really depends on where it is that you're putting your scintillator slab.
And I guess the final one, how selective is the scintillator?
How selective? So let's say the signal you get from a scintillator is obviously not going to tell you the particle identification that you might wish for. It will not tell you this was a muon, this was a proton, or another type of particle. So the one thing that you need to control very well, because that's a source of false triggering, is light. Photons will, obviously, external photons can be incident on the scintillator and transported to the photosensor, or directly incident on the photosensor surface. So the biggest source of, if you like, unwanted signals will actually come from photons in the environment. That is why you need to operate the detector in a light-tight environment.
Okay, great. Let's carry on. So that was our block diagram. And now we're going to take you through the kind of the Museum of Cosmic Pi. So as I said, we started this project several years ago now in October 2014 with the Port's first hackathon at CERN Idea Square. And we built this prototype, which I have here, in a weekend. So we designed it over a couple of weeks beforehand, and we did all the assembly over a weekend. And oops, sorry, just change my pointer. Okay, there's an animation missing, sorry, and it didn't work. So we made many mistakes here. You can see that there's no infill on the board. The DC-DC converter we used is this block here from Murata, which had the wrong voltage range and insufficient stability. It was designed to only cope with a single shot, so we would only have a maximum rate of 1 muon per second. This is one way of designing it. It's a fairly harsh design criteria because it really limits you to the size of scintillator. The scintillators that we use now, we typically get a rate of kind of 2 to 5 muons a second. So having a design that would hard limit it at 1. And the biggest mistake we made was the footprints. So you can see the little spider wires that we have hanging off our chips, which are upside down. This is because we got the footprints wrong when designing our PCB. So we learned an awful lot from this design. We didn't even get the pressure sensor and the humidity sensor working over I2C with the Raspberry Pi, but we weren't discouraged, and we carried on building a new prototype. So this brings us to our version 1. So here you can see the version 1 kind of all mounted in the boards, and this is the enclosure that it would go into. So it's a little aluminium box. And what this comprises is it's an Arduino Duo, which at the time was a brand new, super powerful Arduino, a PCB with all of our ancillary components on it. So it has the DC-DC converters, in fact, in this case, just one channel. It has the GPS module, GPS antenna. That's what this connector here is. Some indicator lights to tell you when there's events. It has the IMU and a humidity sensor and a pressure sensor. The big drawback with this design, so we were using very small slabs. It was cost driven. So this is one of the slabs that we used. It's a 50 by 50 by 10 from Elgen, and it's basically equivalent to a BC408 scintillator. I think we were paying about 50 euros a slab for this. And onto it is mounted 2 advanced SIPMs. And we had a single voltage channel to bias the 2. One of the issues with SIPMs is that the threshold voltages can vary from unit to unit and batch to batch. So it's actually very important in order to get them performing correctly to have the right bias voltage applied. If you over-bias an SIPM, it can become very noisy. The fundamental problem we had with this design was that having 2 sensors on the same channel for the voltage supply meant that one of them was operating correctly and the other one was typically way off into the noise region. So that makes it impossible to use a coincidence trigger because you don't have 2 reliable sources. So there were some major issues with our first design, but again, we learned an awful lot from it. One of the other things is the cost at this point was so high that we couldn't even afford to put a Raspberry Pi in the box for our budget. So that one, I'm afraid, didn't work. From there, we moved on to what we call version 1.5. You'll see our version numbers are a little all over the place. So this kept the same fundamental structure with an Arduino GUI and a board on top, which had all of the extra bits and pieces. And what we did was we redesigned the analog amplifier. And you can just about make out here, there's a couple of connectors. So these are Ufl connectors, which you can see on the slide here. And we hooked this up to external SIPMs, which sits in this little housing here, and connected these to some recycled scintillator slabs, which we were able to get hold of. And there we had 2 slabs, which are stacked on top of each other, and this was the readout. So, oh, I still left my comment to add a photo. This was the first one that worked as a design. We had some major upgrades from version 1, so we improved our analog board, changed the amplifiers. We moved to a 2-channel DC-DC converter. So here we can bias each photomultiplier independently. So if we do have a gap in a different threshold voltage for each one, then that's no problem. For this instance, we moved from advanced SIPMs to Hamamatsu, so it's a different brand. They have a slightly longer track record in producing SIPMs and optical components. We got recycled scintillators, so this saved us enough money to be able to include the Raspberry Pi 0W, which is this guy, which we're actually able to put in the box. So this was our first kind of breakthrough actual working cosmic ray detector that we built. From there, we thought, oh, let's go as far as we can with this to the next stage and optimize it for cost and complexity. So I started building version 2, with some help from the team, and this is one of the version 2 prototypes, and this one didn't work at all. So I think this was probably a step too far. We moved to having a single PCB, which is good. We had 2 microcontrollers. So we stepped away from the Arduino and we went to use the STM32 family. One of them was designed to control the power supply, and the other one would handle particle detection. The other big change that we made here was how the scintillators would couple to it. So instead of having a scintillator with the wavelength shifting fiber, our plan was to take our scintillator and literally just to stick it directly on top of our PCB, obviously with some wrapping, with a little hole. When we built this, we realized that it didn't work. In terms of the coupling, it wasn't efficient enough. So one of the biggest learning points from this design was that an edge coupling to a slab from an SIPM works a lot better than a side coupling in this case. We also had a real problem getting our development environment up and running. It was our first experience using the STM32 HAL, which is the hardware accessibility layer, basically the C libraries that automate some of the functionality for the STM32. So we learned a lot from this design, but unfortunately it didn't work. From there, we tried another version. So this, it just says on the PCB, yet another Cosmic Pi. The idea here was to make a simpler design. And instead of mounting the scintillator slab directly on board, you can see these funny connectors in the slide. These are in fact rotatable 90-degree connectors. So the idea here was that we would have two breakouts where you would solder the SIPMs. You can then snap them off the end of the PCB and plug them in, and then your scintillator would sit in between and be read out at either end. So unfortunately, this one also didn't work because we never received all the components we needed to assemble the full chain. We tried a few innovative things. We learned a fair bit about kind of improving our PCB design, but unfortunately this was not a successful prototype. And in 2017, we tried building one with an FPGA. So here you can see how far we got with the FPGA design. Here's the board. We had 3 or 4 of these made by Seed Studio in Shenzhen. And there's a couple of things missing from this board. The first big gap is the FPGA. Unfortunately, due to an assembly mistake, they were never installed. The other thing that's missing was the ADC. So we thought, let's see how far we can go if we stop the microcontroller, plug it directly into a Raspberry Pi. We'll use an FPGA and an ADC. We'll read out the ADC with the FPGA. We'll do the timing with the FPGA. But due to the fact that there was no FPGA on our boards and we didn't fancy hand soldering this wonderful package, we abandoned it. Likewise with the ADC. The ADC we'd selected and designed around turned out to be very, very hard to get hold of from analog devices. So I'm afraid that was the end of this design. Put a red cross through that, never finished. And this takes us to version 1.6. So this is more or less our current iteration. Here's one of the boards. What we did was we took everything that worked from our version 1.5 and we improved it. We also did away with the Arduino Due and replaced it with an STM32. Again, having a lot more experience with this platform, having gone through a couple of iterations. We changed our SIPMs and we went from Hamamatsu, which are excellent, but also a little bit on the expensive side, to SIPMs from KTech, who very kindly gave us an educational discount, different voltage range as well. And fundamentally here, we changed our mechanical design. So you can see the board has this kind of C shape with a cutout missing. The cutout is actually a riser, which has the SIPMs on it and can be plugged back into the board when you've snapped it off into these 4 connectors here. And the scintillators run in this direction. We'll show you some pictures of the inside. So for the first iteration, in this case, we were able to use a port of Arduino to STM. So basically it's a wrapper. So it meant we didn't have to do much development with our firmware. And we put a little port on the end here to plug in the Raspberry Pi 0W so that it would sit on top of the board. And when we actually assembled this, it worked fine up until we had our first detection event. And the issue is that when we had an event detected, what would happen is that the board would crash. And it turned out to be an EMC problem with the antennas from the Raspberry Pi, the Wi-Fi antenna in particular, which was sitting directly over our main microcontroller, and the two didn't play very well together. So we learned our lesson from that, and you can see the next iteration of the board. We've in fact relocated the Raspberry Pi header, and we've stuck it down on the bottom of the board and also isolated it from the earthing planes. So it's completely islanded out here, and unsurprisingly, this solved our EMC issue. If you're very attentive, you will notice also that the oscillators have changed for the STM. So one of the issues we had with our previous board was that the configuration of the clocks, external clocks for the microcontroller, didn't match the STM dev board we were using. So it meant we couldn't directly port over our prototype code. And basically, this was a problem. So we designed this new board to mirror exactly the configuration on the dev board to make it more portable between dev board and actual hardware using Mbed OS as our preferred operating system. Unfortunately, despite this, it still didn't work. So all the software had to be rewritten again in C using the STM32 HAL. So the EMC issues were solved. On this particular batch, we had some issues with the GPS, which we still haven't managed to identify. Some of the modules failed. We replaced them. Now they work fine. And also some issues with the SD cards in the Raspberry Pi, which we still haven't got to the bottom of. It's ongoing. And the most recent batch that we produced this year was hardware version 1.8. So you can see here's a nice render out of KiCad. And here's our board layout. So we did some optimization and we reduced one of our I2C sensors. We moved from having a separate pressure sensor and humidity sensor into having a single integrated sensor, the Bosch DME280. Also improved the silk screen, some more comments, notes, etc. And we found that in this batch that we built this year, we had a much improved reliability, none of the issues we had in the previous version. So that's kind of where we are with the hardware. It's been, as I said, quite a journey so far. You can see here the list of, I think, everyone who was in the team. Apologies if you were in the team and I've left you out. Hopefully that's not the case. And you can see also the range of different disciplines that we have, physics, software, firmware, electronics. It really takes a lot of people, a lot of knowledge to get to the stage where you have a detector that works. And of course, we wouldn't have got here without some help from people outside of the team who've been really encouraging us. I'd like to thank Marcus Juice and Francois Gray for kind of being cheerleaders for our project and encouraging us. And in fact, the idea for the whole thing, to give credit to Francois, came up from a conversation with Francois back in 2014. So it's been quite an adventure. I'll give you a very brief overview. We won't go into too much detail on the actual circuits. These are all available. They're KiCad files, so it's completely open toolchain. You can download them, you can modify them, you can build your own, or fix any mistakes if you find them. What we've got is over here our STM32. We also have the ESP interface and our Raspberry Pi header. So this is kind of the inputs and outputs and control logic. We have a GPS module. So at the moment we're using Quectel L70, but we recently discovered that there's in fact a pin-compatible, very nearly pin-compatible product from ST. So that gives us two vendors we can use for our GPS. So this tells us where we are and when we are. In here we have our pressure and humidity sensor, and also our accelerometer, magnetometer, gyroscope connected over I2C bus. This block up here is our trigger. So we have some AND gates and some Schmidt triggers, which basically look for a pulse above a certain threshold. These are comparators. So you can set a detection threshold. Any peaks in voltage above this threshold will trigger each channel, and then we AND the channels together. And when we get a signal on channel 1 and channel 2, so that's a detection in both of our slabs within a very, very short time window of a few nanoseconds, we trigger this 555 timer. So those of you who are electronics geeks will know that the 555 is one of the oldest and most well-known semiconductor chips there is. And we use this to stretch out the pulse. So the signal that we get out of our AND gate is literally a few nanoseconds long, but with a 555 timer, we stretch it to make sure that it is at least 2 clocks of our microcontroller in length. This means that when we send it as an interrupt, we can detect it reliably. Anything less than that, there is a risk that the microcontroller will miss it as an interrupt, and that would be a cosmic ray, which we didn't capture. We also duplicate this circuit for channel 1 and channel 2 independently. So this means that when we're building the detector, we can also do some calibration. So we can look at signals from one channel independently of the other channel, which helps us to tune for the rate and also to make sure that we don't have too much noise. And down here, we have a power supply and some LEDs on the front panel. So we feed the Raspberry Pi at voltages up to 12 volts, AC or DC. We have a little cap here. Again, this is something that we learnt. The 1.6 generation doesn't take an AC feed, it only takes a DC feed. If you plug an AC feed in, you break it, but we fixed that, and so there's a protection diode and a capacitor. So versions 1.7 and 1.8, you can plug in either an AC or a DC power supply. And we regulate that down to 5 volts, which is kind of the power voltage. It feeds the Raspberry Pi, which has its own regulator, and it also feeds our DC-DC step-up, because we get more efficient conversion if we start with 5 volts rather than 3.3. And then we have a 3.3 volt converter here, which drives some of the lower voltage logic, and also STM microcontroller, which is the 3.3 volt part. We have a second page of schematics, and that's it, so 2 pages. And on here, we have a high voltage bias supply. So we're currently using the MAX 1932, which is an SPI addressable step-up converter. It's 8-bit, and this means that we can digitally set our voltage, and it's compensated. So this gives us full control from software over what voltage we put on our SIPM sensor, and it means we can kind of adjust that as part of the calibration process to get a nice balance between gain and noise, enough gain and not too much noise. Over here we have our analog amplifiers. So we have 2 op-amps, which are in it's a dual op-amp package from Analog Devices, ×2, so one for channel A and one for channel B. And then we also read out in the middle, you can see this tap here, the signal, and we put it through a shaping stage, which is down here, for a slow pulse, which is connected to the ADC of our microcontroller. The STM32 that we use has a 1 megasample per second ADC. So we've geared it up so that we could read it out. At the moment, that's not something we've implemented in firmware, but it would be nice to see the signal from the cosmics that we determine. We have light injection. So on our riser board, which connects to the slabs, we have some blue LEDs, and this enables us to test and to simulate cosmic rays by flashing blue light into the scintillator, which would then be captured by the SIPM. So we can use that to validate the system works. Again, it's not something which is implemented in firmware. And finally, because our analog systems are fairly sensitive to noise, we run them off a dedicated rail. So they have their own power converter separate from the 3.3, so they're not subject to the noise that gets onto the rails from the microcontroller as much as possible. So that's it for the circuits. Scintillators. So our version 1, say, used this 50 by 50 tile from Elgen. For our version 1.5, we used some slabs which were recycled from a physics experiment, which had wavelength shifting fibers. And we took them, we cut them in half, we put them on top of each other, and we did coincidence. But from version 1.6, we've been using these slabs that you can see in the picture, which are polystyrene. They are 200 millimeters by 100 millimeters by 10, and we can order these. So one of the biggest challenges in the project was finding someone who would sell us scintillators as a very small group of people trying to build a detector rather than a giant enterprise. So this was really good, and we've been very happy with the scintillators that we've received from Amcris. They've changed their name to ISMA recently. So we take this slab, we wrap it in tinfoil. We started off using a very thick industrial grade foil, but we've now moved to literally using kind of domestic tinfoil to wrap them. the other special thing, so you can see the two holes which I've highlighted on the slab here. So we get our scintillators pre-drilled with two holes in them, which we then epoxy a grub screw into, and we use that to mechanically fix our SIPM board to the scintillators. It's not an ideal way of fixing it, but we find that it's actually quite robust and it works reasonably well. So that's the story of our scintillators. And of course, it would just be some electronics on the desk without an enclosure. So our very first enclosure was this really nice, shiny aluminium box from Hammond. And we had the faceplate custom machined to have the holes in it for the Arduino and for our GPS and for our indicator lights. From there, we moved on to a plastic box to allow us to fit bigger scintillators, and also to ensure we didn't have any unwanted shielding effects from the aluminium when we were able to integrate Wi-Fi. So this is the part from Hammond that we use now. It's a large plastic box. And again, we have a custom machined faceplate, so with some holes in it, so that our electronics pokes through and you can plug in the power supply and the USB if you want to, then the GPS, and you have the lights that tell you when it's detecting. So this is what our enclosures looks like from the front. So we just print out a sticker with a laser printer and stick it to this panel, cut the holes out. You can see this was our version 1.5, and this is 1.6 and 1.7 and 1.8. So we've changed the front panel a little, but not a huge amount. I'm pretty happy with how it looks when you laser print the sticker, cut out the holes and stick it on. And then when you take the lid off, this is what you see inside. So here we have our two scintillators. We have some plastic, just cut C profile to hold the scintillators in place, and a piece of packing foam just to stop any movement because it's not restrained in this axis here. And then we've got our Raspberry Pi in its new position here. So this is the faceplate. So these holes are made for us by Hammond as part of the manufacture. And then this is what it looks like inside. The PCB sits on side bosses, which are molded into the case. And here you can also see the SD card in the Raspberry Pi. So you don't need to completely disassemble the thing in order to change the SD card. You just take the lid off and you can change it. Onto the firmware. So our original firmware for the version 1 was written by Julian Lewis, and we still kind of use all of the core concepts that he developed whilst building that. It was modified by Hendrik for our version 1.5 with some changes to the way the hardware was constructed and some changes to the way we did the output, ready to be hoovered up by a Raspberry Pi, listening on its UART port. We were very lucky for version 1.6. We could basically take this firmware and port it straight over to an STM32. We changed the pinouts and that was about it. And then from version 1.7 onwards, we've moved back to using STM32HAL embedded C with initially Eclipse on the version 2, and now ST have their own version of Eclipse with a wrapper on it, specifically for STM32 development. So I had the pleasure of writing the firmware for version 1.7, and a lot of that was also based on work done by one of our students, Sabri, who wrote the version 2 firmware for the aborted attempt at doing that. In terms of what the firmware does, obviously it initializes all of our hardware peripherals, the DC-DC converters, the I2C, the thresholds for detection. It has a calibration mode, so you can set the pin on boot, which will take you into calibration mode where you can store values in the flash of the microcontroller for detection thresholds and also for voltage settings. When it turns on, the biggest weight is for the GPS to acquire. So if you've used GPS even on your cell phone, you'll know that when you go straight into your Maps application, it doesn't tell you necessarily exactly where you are. It can take a couple of minutes for the GPS to acquire some satellites. So we can't start doing any cosmic ray acquisition until we have a fix because we need it for the timing information. When we have the GPS running, we then start one of the timers. So the STM32, the reason we chose it is because it has an 82 megahertz or 84 megahertz core frequency, and it has a 32-bit timer which runs at 40 megahertz or thereabouts. This gives us a very high precision, and we actually have basically the same timing precision we had with the original Arduino firmware by Julian, which is about 65 nanoseconds. So if we have a cosmic ray detected, we can fix that in time relative to UTC to plus minus 65 nanoseconds with a very precise timestamp. And when the device is running, so basically it detects events with an interrupt. So when we have a coincidence, there's an interrupt to the microcontroller, it will read out its timer value and store that in a register, and it keeps storing them until we get a GPS. PPS stands for pulse per second. So this is a typically plus minus 15 nanosecond signal that comes out of our GPS receiver chip. And this is another interrupt, and this one reads out our event register, so all of the timestamps. It also triggers the readout of other sensors, the IMU, the humidity sensor. We also read out the GPS latitude and longitude and the UTC timestamp. And all of this is put asynchronously out on the UART, and the timer loop is reset, and we reset our event counter to 0, and we do another second. So this is kind of the main loop for our firmware. And that fundamentally hasn't changed since version 1. From version 1.5 onwards, we have a more sophisticated, we have kind of high-level software. So all this runs on a Raspberry Pi. We have a local SQLite database, which is stored on the SD card. We also publish events via MQTT, which is a protocol very simple for Internet of Things applications. And we share all this with the users over Wi-Fi. So from version 1.5 onwards, we create a Wi-Fi hotspot when you power up the Raspberry Pi inside the box, and you can connect to it with your laptop, your smartphone, without it's a fully wireless connection. And so we serve our data over web. We have a REST API. It's written in Node.js. We have some basic information we put up, and we also allow export of data, and you can connect your Cosmic Pi to your local Wi-Fi network through the web interface. So you can feed it in the SSID and the password, and it will connect. All the code for our kind of user-facing stuff is also on GitHub. Here's the link if you want to check it out. And this is what it looks like. So we have some nice graphics that match the front of the box. Here we have the most important thing, which is our cosmic ray data. So this is a histogram, and it automatically updates every couple of seconds, showing you how many events were detected by your detector within the last few minutes. So typically this is fairly normal. We have sometimes where we have less than 2 events. We have sometimes occasionally up to 6 events per second. We show the GPS location through Google Maps. And then we read out all the other sensors. So we have a temperature sensor on board, humidity, pressure sensor, acceleration. So here we're more interested in orientation rather than acceleration, this being the G. A magnetometer. So we read out the orientation relative to magnetic north, and this would also tell us if someone had decided to set up their detector in a magnet or next to a transformer or something else. And then we have our version number. So this is dependent upon the hardware, and also a unique ID. So this is this must be a 64-bit identifier unique to each Raspberry Pi. So it gives us a way of saying, you know, this unit is number this much, and that's a completely unique identifier. And then finally, we've got the GPS location. So this is kind of the dashboard, and it automatically updates every couple of seconds. We have some extended functionality under our Science tab. So here you can custom build your own histograms, or you can download the data as a CSV. So you can process it locally in Excel or MATLAB or Python, whatever the tool of your choice is. In terms of how this looks, so on boot, we use systemd in Raspbian, now Raspberry Pi OS, to run a bunch of different services within the Raspberry Pi. So we run a service that is basically database maintenance. It just keeps the database neat and prevents it from being corrupted. We run a detector readout. So this listens on the serial port of the Raspberry Pi for the data which comes from the STM32. So every second, the STM32 just spits out any cosmic rays which were detected and all of the timestamps. And then these are caught by the Raspberry Pi and put into the database. We have our user interface. So we have a web server which runs, and we also have an Mqtt Publisher. So Mqtt is a publish-subscribe model. So a Cosmic Pi is a publisher. It connects to our server and publishes events with a slight offset from real time. So there is a variable delay of up to 30 seconds. The idea behind this is just to make sure that we don't get our server overwhelmed with all of the requests arriving simultaneously, and that there's some staggering. And then we have our Wi-Fi module, which is our gateway to the outside world. Kind of how this interfaces, so we have the hardware UART, which communicates with our microcontroller, which puts the new events in. The new events then are spit out via HTTP, the web interface, over Wi-Fi, and also over MQTT. So these are independent. And then these go to our server. And then through the Wi-Fi, our most recent version, we serve an access point. So when you turn it on, you see Cosmic Pi Wi-Fi, which you can connect to. And we can also support a simultaneous network connection. So you can bring it to your home or your school. You can give it your network credentials, and it will connect to the internet whilst also providing a localized hotspot, which is secured with a password. And that also bridges. So you can, when you do this, you see the Google map filled out. One of the issues with operating it in standalone mode is that Google Map is not cached. Kind of the final piece of the software puzzle. So I mentioned we have an MQTT server. So each detector, when it's connected to the internet, will connect to our server and will publish its events. The theory being that we can store these in a central database, and then we can have a global web dashboard, which enables you to see all of the Cosmic Pis in the world and all of their events, and also to download some or all of the data. Unfortunately, so far, we've only got to the level of having a live MQTT server. This is still a work in progress. So to finish up, here's a, as promised, review of the costs. So this is from our most recent production run, where we built about 20 units this year. And these are what the components cost. So the main cost, as you can see, is in our PCB. And this includes the board itself, the purchase of all of the components on the board, and the assembly. So there's quite a lot in that. And it's the main area where we've been focusing on trying to reduce cost. For example, going from 2 I2C components for pressure and humidity down to 1. That saves us a couple of dollars. There are more areas, for example, the Max 1932. The chips cost about $9 a piece. So that's $18, looking for a cheaper solution there. Piece by piece, in the future, we should be able to reduce this a little. But again, we're not going to get kind of 100% reduction in this cost. It's still going to be probably the largest cost. At the moment, we're at about 350 Swiss francs a unit. And this is only materials. So what you also have to factor in is the time that it takes to take your scintillators, to wrap them, to put in all the screws, the nuts and bolts, check the housing, make sure that it all fits together, calibrate it, test it. But it's still, we think, a very cheap solution. And this buys everything. So you don't need to have any other pieces of hardware to start. You can literally start with nothing at all and build a cosmic detector like this. And I think that's all the content we have for today. So are there any more questions? Do we have a target price and a market, from Andy again? So this is kind of our long-running goal, and those of you who've seen our TED Talk, is to have to be able to crowdfund this detector. For those of you who kind of follow electronics and people crowdfunding their latest gadget project, typically you need a very good gross margin. When you do a Kickstarter campaign, a lot of things go wrong. The thing that you thought you were going to buy for $5 turns out to be $10. So it's very important to have a cost margin. And really kind of at the moment, we've been working on getting the platform stable, getting all the bits and pieces developed, trying to engineer out cost incrementally from our design. I don't think there's much of a demand, maybe I'm wrong, for $1,000 cosmic ray detector. When you think about the kind of the actual costs, taxes, etc., if you take this $350 detector, by the time you productize that and ship it and have some contingency in there, you're looking at about $1,000 probably, certainly 700, looking at kind of a gross margin of 100%. So basically, we kind of, for me, it's still a bit too expensive to go to that crowdfunding level. But I think that that's still our goal to have this. And in terms of the market, for me, it's anyone who's interested in having a cosmic ray detector, which hopefully is quite a few people. It's not for everyone, obviously. There's also a big educational market. But again, that is geared around having a lot of the support materials. We can give you a cosmic ray detector, but as a teacher, you receive it. Okay, it's a cosmic ray detector. It has lights that flash. In terms of providing educational materials that kind of as a wrapper around this, that mean that you as a teacher, every single teacher who gets one doesn't need to write their own lesson plan completely from scratch, is another kind of key enabler to getting into the education market, I think. I don't know if you have anything to add.
Well, I think, no. We've discussed this several times. There is one question, which is actually a very valid one, about the minimum batch size to keep costs relatively low. That's coming from Dimitar Kolev. Maybe you want to answer that one. It is a very important question, actually, because, yeah, go ahead, James.
Yeah, so when we first started back in 2014, the batch size that you needed to kind of mass produce and to really get the cost down was in the order of 1,000 units. In terms of PCBs, the scaling, the way that the kind of the electronics industry, and likewise, we had great difficulty getting manufacturers of scintillators to even respond to our emails because we're asking for such a small quantity. Now the market has evolved, and basically the price breaks for going from building 20 boards to building 1,000 boards, it's actually not that great. It's maybe 5, maybe 10%. So it's something, but it's not kind of make or break. Likewise, we've been very lucky to find ISMA as a partner who will produce us a batch of 70 scintillators if we want. So from a kind of artisanal, homemade production point of view, there really is not a kind of a bottom limit on batch size. In terms of manufacture, that's not really something we've explored. I would stress that there is a big labor component in terms of wrapping the scintillators. This is not something which you can do without, and it is quite a specialist job to get right. It takes some practice. Any mistakes in it, and your detector isn't going to work. So it's a make or break issue. To respond to the question from Elias, do you look at using a flip-flop instead of a 555 timer? Yes, I mean, in theory, we could use a flip-flop and then we could have it reset. We didn't really consider this in our design. The other thing is minimizing the load on the microcontroller. So not having the microcontroller drive an external output as part of its detection loop minimizes your dead time and your variability in terms of time and performance cycle to cycle. But I mean, yes, there are other solutions. Our solution is it's a bit deluxe and expensive, but it's also simple and it works. Maybe another question from Dimitar. One more. How many sensors across the world, or say initially Europe, would be enough to get consistent data, or to get a good dense network? Etam, do you have any?
Right. That's a very interesting question. You've seen the size of the plastic scintillator. So one single cosmic pi unit is just a few 100 square centimeters, right? You would need to cover a typical, for example, one of the interesting things you might want to do is just capture fully a cosmic ray shower. All right, depending on the initial energy of the cosmic ray, this shower can extend over several square kilometers. So I think ideally you want to cover the surface of the Earth or whatever area, Europe, with our cosmic pi scintillators. This is obviously not possible. Many projects worldwide are really that greedy, right? IceCube is probably one of the biggest detectors in the world, and here you basically place your photosensors. Again, these are photosensors that detect photons in ice over several cubic kilometers of ice, and so everybody would, I mean, physicists would just love to be able to do that, but in reality, this is not possible. Now, it's to get a good dense network, you would need. Well, it's difficult to put a number on it. Really, it is very difficult, I think. At the level of a few thousand sensors, what you could do is have these sensors in different places. The best way to optimize that is to bring the sensors together, okay? Yes, sensors per square kilometer. One way to do it is to bring people who do have the sensors together within an area, so they can actually collect data for, I don't know, a few hours, and see if they can essentially trigger on a shower. So receive muons simultaneously across several square kilometers, and that will give you some idea. But in practice, the efficiency is probably going to be very, very low.
I guess, yeah, it's difficult to answer that question until someone has built a giant I mean, IceCube is pretty big, but it's still kind of only a very small portion of the Earth's surface that's covered. You'd need to cover a large area to figure out how many you need.
Well, that's an interesting calculation to do, actually, making a hypothesis about how many people have these sensors, maybe 100 sensors or so. We know the locations, and then try and estimate how long it would take in time. It's a question of time, essentially, to be able to detect a shower. So if you lend or borrow a detector, and you have several hundred of these detectors in a certain area, how long would it take to detect a shower?
Interesting events with finished cosmic pies from Stephen. No, I'm afraid. So at the moment, we have our server live, but we are not recording the data. We haven't yet got the database set up. So I'm afraid all of the events are broadcast in real time, but no one is recording. That's something for us to do in the future. We don't have very many units. So one of the kind of the more user issues is the units that we ship. So far, all the ones we've built have been predominantly for beamlines for schools, which is a CERN-run competition. And the winners get to come to CERN and use a beamline, and the runners-up get sent a Cosmic Pi to their school. But the way that they tend to use them is not to leave them plugged in and connected to the internet and broadcasting their events to us. They tend to use them periodically for a few hours here, a few days there, but not to leave them continuously connected. So that's kind of also I guess an issue for us to think about in terms of, you have this idea, oh, we're going to build this thing and it's going to be used in this way, and then you give it to a real person who is not involved in the development, and they say, oh, this is great, I'm going to take it and I'm going to use it for this other slightly different use case which you didn't think of. So I think there's a kind of a communications message we need to work on one side, and also an infrastructure on the other side in terms of logging all that data and making it available. We have another question from Andy in the chat. Do we have a target price market? Are there any research projects who need this kind of data? So in terms of research projects that need this kind of data, from a commercial point of view, I'm not really aware of any commercial applications of cosmic ray data in this form. Obviously, space weather and conditions affecting satellites is a business, or at least is a commercial service, or a service with commercial applications. And ESA provide that information for free. They have an app you can download that does that. I know also that I think there's some interest in data centers in putting scintillator tiles in the top of the rack to see if muons or cosmic ray showers are causing crashes in servers. But beyond that, I'm not aware of anyone who's using this, Etan.
I think, as Nikolai has answered here, it's a very good answer. It's a detector that's very interesting as a, let's say, a tool for hobbyists or an education tool. James, you mentioned, I mean, yeah, the potential for using maybe cosmic pi type detectors, scintillator type detectors of that scale at least, to maybe monitor muons. In terms of, I think one of the initial questions was about research projects. So research into cosmic rays, generally for the purposes of, let's say, fundamental physics, gets done in space these days with typically spaceborne experiments.
For example, AMS.
Exactly. That is where you will, which is on the International Space Station. That is where you're going to be getting the cleanest signal of cosmic rays. Once you are on the Earth's surface, or at least partway through the Earth's atmosphere, you're, let's say, corrupting already some of the information. So, as James mentioned, there are some reasons to study cosmic rays for other applications. We know, for example, that they affect electronics. Okay, you have various radiation effects which are caused by these cosmic rays, usually away from the atmosphere, but they can also happen partway through the atmosphere. At ground level, it's much, much rarer, I think. So it really, I think, for a research project, that will really depend on the number of units you can deploy. You have other ideas, muon tomography. So this is basically using muons, which can penetrate materials quite, let's say, through several meters. So the idea is to use muons essentially to look at the internal structure of buildings or objects generally. I mean, the idea was first, I believe, really demonstrated in the 60s with Alvarez, who was a Nobel Prize winner in physics, and he used muon detectors. So he did do muon tomography on pyramids to search for hidden, let's say, cells in pyramids. So that's something else you may be able to do if you put enough of these cosmic pi units together. So there are some possibilities.
Nikolai brings up a good point in terms of research project on a really small scale. So one of the best experiments you can do is actually to take your cosmic ray detector and to put it on a high altitude balloon and release it from the surface of the Earth, and you can see how the detections increase as you go up. And this basically is recreating the experiment of Victor Hess when he discovered cosmic rays. So that is kind of something you can do with the cosmic pi detector. Obviously, you need to put a battery in your balloon and a parachute to make sure it doesn't land on anyone's head. But a question from Lucas. How many stations are live 24/7, and how do we animate our users to keep them running and sending data? So it's a very good question, and we don't have an answer to it. We don't have any stations that are continuously live 24/7. We have some that come and go as people turn them on and off. And yes, we're looking for ways to motivate and encourage our users to keep them running and keep them live. So if you have any answers to share, then they're very welcome. A question from Stephen in terms of, have we come up with any novel use cases or methods, or have users come up with any that we haven't thought of as developers? Not that they've shared with us to date. One of them kind of more interesting areas that I think I would personally like to look at is the interface between climate and cosmic rays. So the cosmic ray flux is affected by the atmosphere. So in theory, with our pressure sensor, we can measure how much air there is above the detector, and we could look at whether that has any bearing on the cosmic ray flux. Also, we have the magnetometer, so we can look at potentially variations in the magnetic field and how that would affect the flux. But these things you need a lot of data for, and we're only at the stage of having made reliable units that can detect these things. Then we would need a lot of units and a lot of time and a lot of data in order to be able to look at things like that. Final question on the list from Wojciech. How do we position ourselves in respect to QuarkNet? Itam, I don't know if you have anything to...
QuarkNet, yes. Well, we first of all, we're not direct competitors to anybody, right? Now, QuarkNet have, yes, got a system that looks very interesting. I do not know if they have any upgrades, and I haven't been following their progress lately, but the system they had at least a while ago was based on plastic scintillators read out by photomultiplier tubes, which are very different to silicon photomultipliers. Photomultiplier tubes are much more bulky. They require much higher voltage to operate, typically in the kilovolt range. So you can immediately tell for, let's say, as an educational tool or an object that would be distributed in schools, it becomes a lot more complicated to distribute something that has, I don't know, that operates with 1 or 2 kilovolts to sense photons. This is the type of tool that would typically be used by physicists, even now, almost daily, right? We use exactly that sort of setup to calibrate our detectors or to test our detectors. So we're used to using that type of device in labs. But I don't know how QuarkNet really, whether they have the same sort of market or as we do. I don't think so.
So maybe, yes, so again, I haven't checked up on the progress of QuarkNet in several years since we started the project. One of our kind of drivers was to use current technology. So a lot of the cosmic ray detector projects out there use recycled designs from physics experiments. The downside of this is that very often they're using kind of end-of-life or old components, so FPGAs or DC-DC converters, or just kind of pieces of the architecture. So that was kind of one of our key drivers, was to build something using common pieces, no legacy elements, kind of cutting-edge technology, not super cutting edge, but commercially available. So that was kind of, I guess, something maybe that certainly at the time we started it differentiated us. I don't know what Quadnet have done recently. It would be good to catch up. Dimitar, say one major milestone is to build and put up 1,000 pieces. Yeah, that would be a great milestone. I think we're a long way. One thing that I would say that this product has taught me an awful lot about how to build a cosmic ray detector, but I mean also about how to build a circuit and design a circuit and make something that works reliably. It's also taught me that building one cosmic ray detector yourself with your own hands is great fun. Building your 100th cosmic ray detector with your own hands gets to be a little less fun and a bit more repetitive. So I think one of the pieces of getting 1,000 units built is coming up with a way to do that, whether it's a kit that you can assemble reliably wherever you are in the world, or whether it's finding a commercial partner to wrap the scintillators and to do it, and a way to pay them for it. Maybe in some research program like Eurostars can be a source of funding along with some SMEs. That's not really something we've explored. Our ethos is to make it open, so open hardware, open software, rather than going down a kind of purely commercial road. It would be nice to see if we can in the future do something where it's kind of like a crowdfunded participatory finance project, where it can be sold on a commercial basis, produced by a company, but still remain open. So I think if that is everything. Yes, a good point from Nikolai in the chat. So the OHL that we've used doesn't preclude commercialization. If anyone in the audience happens to be a manufacturer and is interested in manufacturing our device, please do get in touch. You can take what we've done and make it an open product, and we might be interested in buying it back from you. So that's one of the opportunities that having an open ecosystem creates. So unless there's any other points, I think we'll close up. Thank you all for coming and listening and for sharing your questions. And this, as I said, will be available online. So if there's anything you want to catch up on, you'll be able to find it. I think I'll put it on my YouTube, and also links to our Facebook and on our website. And of course, if you think of any other questions, please get in touch. You can get in touch through our website, cosmicpi.org. So have a good evening, everyone.